Welcome back to Laplace transform. We are still in chapter 2, where we try to find Laplace transform of some functions and the inverse Laplace transform of other functions. So we will go back again to slides. We finished last time with example number 5. So we will continue this from chapter example number 6. So in this example, we have this function f of s equal 2 divided by s plus 1 multiplied by s plus 2 square, and we need to find inverse Laplace transform of this function. So in fact, it's 2 divided by multiplication of 2 terms, but one term is higher order. So it's we have roots which are real and repeated. So s plus 2, it's real, roots are real and repeated. So to solve this one, we will use partial fraction expansion. So we will say that, okay, this one will be the summation of k1 divided by s plus 1 plus k2 divided by s plus 2 squared, just remember, plus k3 divided by s plus 2 square root of that term. So it will be the summation of those 3 terms. We need to find the k1. If you want to find the k1, just multiply the other side by s plus 1. When we do this, when you multiply by s plus 1, this part will disappear and substitute hs by -1. So it will be 2 divided by -1 plus 2 squared, which is 1. So it will be 2. So in fact, k1 equal 2. We will do the same for k3. If you wanted to do it for if you want to do it for k2, so in this case, we will multiply the other side by s plus 2 square. So s plus 2 square will disappear, and it takes the limit as s equal -2. So it will be 2 divided by -2 plus 1, which is -1. 2 divided by -1, it's a -1. So in this case, k2 will be we said -1, -2? Yes, -2, k will be -2. So now we can find the k1 and the k2, but it's difficult to find the k3, because if we will do the same, and if I try to multiply the other side by s plus 2, we will have that part disappear, but we still have s plus 2. And then when we substitute s equal -2, that part will be 0, and it will be 2 divided by 0. That part will be infinity, right? So it will be impossible to solve for k equal 3. So what should we do in this case? So in fact, we just need to multiply both sides by s plus 2, so we avoid having this infinity problem, and it takes the first derivative of this equation with respect to s. So we will go, when we are solving for k2, we got this equation. I mean, when we are solving for for k2, we got this equation here, multiplied both sides by s plus 2. So it will, the left-hand side, it will be 2 divided by s plus 1. Here we will have s plus 2 squared divided by s plus 1 plus k2 plus s plus 2 squared divided by s plus 2. If you substitute s equal -2, this part will be 0, right? So this part will be 0, it will cancel. And also here, this part also s equal -2, this part will be 0. So what will remain will be k2, correct? k2 equal 2 divided by s plus 1. When we set s equal -2, so it will be 2 divided by -1, so it will be -2. So now we can get the k2. But to solve it for k3, you need to differentiate that part with respect to s. So just to simplify it, so it will be 2 divided by s plus 1, s plus 2 squared divided by s plus 1 multiplied by k1 plus k2, plus this one will cancel this one. So it will be s plus 2 multiplied by k3. Take the first derivative of this equation with respect to s. So if you want to do this, in fact, so just imagine that this one will be 2 multiplied by s plus 1 to the power of -1, right? If I want to take the first derivative of that part, so it will be -1 multiplied by 2. So it will be -2 multiplied by s plus 1 to the power of -2. So it will be -2 divided by s plus 1 squared. So this is the first derivative of this left-hand side part. When you take the first derivative of k2, that part will be 0, so k2 will disappear. When you take the first derivative of that part, k3 is constant, and the first derivative of s plus 2, it will be just 1. So in fact, that part will be k3, right? So what is remaining for us is this part. How can we take the first derivative of this part? There is a way, in fact, there is way for doing this. It's a function. When you have a function called u divided by v, so this one, in fact, you can say that, okay, this one, it's like u divided by v. And when we take the first derivative of that part, which is d by dt of that part, it will equal, in fact, u dash, the first derivative of u multiplied by v minus u multiplied by v dash divided by v squared. That is it. So now we need to get the first derivative of that part first. So it will be 2 multiplied by s plus 2 and subtract 1 from 2. So it will be just s plus 2. First derivative of s plus 2, it will be just 1, right? Minus u, which is plus 2 squared multiplied by the first derivative of the denominator, which is 1, divided by s plus 1 squared. So it will be like this one. And that is enough, right? This is very enough. Because in fact, we will take the first derivative, and after that, we will take the limit as s go to minus 2. And then when s equal minus 2, that part will be 0, that part will be 0. So in fact, the k1 will disappear. So what will remain here, in fact, in reality, it will be k3 equal minus 2 divided by s plus 1 squared. Take the limit as s equal minus 2. So it will be minus 2 divided by minus 1 squared. So it will be minus 2 divided by 1 equal minus 2. So it will be just minus 2. So now we did it. So in this case, k3 also will be minus 2. So I will go to the next slide. I don't know if you can see my, hope that you can see my, my drawings. Yes. I don't know, maybe I had a problem, in fact, in because I used the annotation. I have no idea if you were, if it is recorded. So now k3 equal minus 2. So we can just write our function as f of s equal, it will be like this one, 2 divided by s plus 1 minus 2 divided by s plus 2 squared minus 2 divided by s plus 2. If we need to convert this one into time, so f of t will be, means the first term here, it will be 2 exponential minus t minus 2 exponential minus 2t, but remember this one, it's a square, and when it is a square, you need to multiply it by t. Minus 2 exponential minus 2t. So you can see that the whole function consists of a natural component, right? We don't have any forced component in this one. And if you want to simulate it in the time response, using Python, for example, you will get this response, right? So at initial conditions, at t equals 0, the output will be 1, and after that, it will go down to 0 when time go to infinity, right? So as t go to infinity, f of t will be 0, because all exponentials are negative exponentials. And the solution of the function, it's just all natural component, because we don't have any input, we don't have any forced component in this example. Okay, so now we can go to this next example. Example number 7. So we need to find the denominator of f of s is complex and imaginary, right? So this is another example also. And if you look into it, it's a 3 divided by s multiplied by s squared plus 2s plus 5. Okay. So this one, it's complex. I mean, I need to select a different color. Okay. So as you can see here, that part is, it's complex and imaginary. So if you want to simplify it, if you want to find its roots, you need to use the law, correct? Second order system, it's a 5 times 1. So it's impossible to simplify it more. So in this case, we need to simplify it. So in this case, we will use partial fraction expansion. If this one is a second order term and it's complex and imaginary, you cannot simplify it more. So we need to write the partial fraction expansion in this form. So it will be K1 divided by S plus K2S plus K3. So that part should be first order system divided by second order system. Because I don't know if this one will be K3 or K2S plus K3 or not. So we need to define that part as a first order system as 1 degree less. So it will be 1 degree less. So this one will be S squared plus 2S plus 5. So the upper part here, it will be K2S plus K3. Now we need to solve it. K1, it's easy to find it. So if you want to find the K1, just multiply both sides by S. So S will disappear and set HS equal to 0. So K1 will be 3 divided by 5. It's easy. K1, it will be 3 divided by 5. Yes, K1, it will be 3 divided by 5. What about K2S plus K3? Now, to find this one, we will multiply both sides by we need to just simplify it and we will solve it, right? So we will multiply both sides by the denominator here, which is S multiplied by S squared plus 2S plus 5, to simplify it. So when we do this, in that side, it will be 3 equal K1 multiplied by S squared plus 2S plus 5 plus S multiplied by K2S plus K3. So we have this equation. Arrange it. So it will be like coefficient of S squared. We have here K1 S squared. We have K2 S squared, right? So it will be K1 plus K2 multiplied by S squared plus coefficient of S, it will be 2K1. And here S K3, so plus K3 multiplied by S. And plus, we have here 5K1, 5K1. So this one equals 3, in fact. So in fact, when you compare the coefficient of both sides, you can see that coefficient of S squared equals 0 because we don't have S squared on the other side. So we can say that, okay, our first equation will be K1 plus K2 equals 0. This one will be my equation 1. Coefficient of S, it will be 2K1 plus K3 also equals 0 because on the other side, we don't have any coefficient of S. So we need to solve those equations, right? Remember that we know K1. If you know K1 from equation 1, you can get K2. So from equation 1, we can say that, okay, K2 equal minus K1 equal minus 3 divided by 5. Now we can get K2. From the second equation, we know the value of K1. We need to get K3. So in this case, K3 equal minus 2K1. So it will be minus 2 multiplied by 3 divided by 5. So it will be minus 6 divided by 5. So now we can solve it for K3. So now we have K1 and K3. So just substitute those values and try to go to the table and find something closer to this formula for find inverse Laplace transform. So now we will write it. So if S will be K1 divided by S plus this one, substitute those values, try to simplify and try to find something closer to this form from the table. So when we look into the table, we can see that, okay, we have this equation here. It will be S plus 2 divided by S squared plus 2S plus 5. So in fact, if you look into the table here, we need to get S minus 1 square, S minus 1 square, B square, right? We need to get something similar. So that part here, we need to make it similar to this one. So it's S squared plus 2S plus 5. So in fact, we can make it S squared plus 2S plus 1 plus 4, right? And that part will be S plus 1 square. plus 2 square. When you look into it, so now A equal minus 1 and B equal 2, in fact. So in the above here, we need to have B. So I have here S plus 2. So, and I have here S plus 1. So if you look into that part here of this cosine, I need to have S minus A also. I have here S plus 1. So on top here, I need to get S plus 2 as well. So S plus 2, I will divide it into S plus 1 plus 1, right? So it will be S plus 1 divided by that part. S plus 1 divided by that part, it will be converted into exponential AT multiplied by cosine BT. What is remaining on the other side, it will be 1 divided by S plus 1 square plus 2 square. But remember here, I need to get B, because this one is B, I need to have here B. So I need to multiply here by 2 and divide outside by 2. So it will be like this one, 2 dividing here by 2 as well. So in this case, the first term here will be converted into exponential minus t. This one, it will give me exponential minus t multiplied by cosine bt, which is 2t. And that part here, it will be in fact half multiplied by exponential minus t multiplied by sine 2t. Now we can solve it. So just arrange and you can get the final form. It will be f of t, it will be 3 divided by 5, because this one, it's 3 divided by 5 by s. So in time domain, it will be 3 divided by 5 minus 3 divided by 5 multiplied by, take exponential minus n minus t common factor. So it will be minus 3 divided by 5 exponential minus t multiplied by cosine 2t plus half multiplied by sine 2t. So now we can solve it. So in fact, this equation, it's very, very complex. And if you want to solve it for f of t, it will take huge of time. But if you can use Laplace transform, it will be much, much easier. So now we can go to the next slide. So I just asked you to visualize the response in Python. So when you look into the function in S domain, this is the function in S domain. This is how it looks like in time domain. You can see we have forced component here. We have 3 divided by 5. This is the forced component, which is due to the input, minus 3 divided by 5 multiplied by exponential negative. This exponential negative, it will decay over time. And we have cosine 2t and the sinusoidal, right? So we will have this overshoot and undershoot, right? So when you look into the response, you see that at steady state, my output will equal 0.6. 0.6, which is 3 divided by 5. 3 divided by 5, it's 10 divided by, sorry, it's a 6 divided by 10, which is 0.6. So my output at a steady state, it should equal to 0.6 minus, this is a natural component, minus 3 divided by 5 multiplied by exponential minus t. So the whole part will decay over time, right? So it's exponential. So it will start from 1, it will go down like this one. But because I have some cosine and sine, it will add some overshoot and undershoot. So the overshoots and the undershoots here, it's coming from this term, cosine 2t plus half multiplied by sine 2t. So this is how it will work. So plot the function, and if you want to plot only the natural component, as you can see, this is a natural component. In fact, it's exponential negative. You see this red line? It's e minus t. But because it's multiplied by cosine 2t and sine 2t, you will have this sinusoidal impact. So in fact, it's exponential plus multiplied by this impact. So it will generate this undershoot and overshoot, right? So this is how, and of course, this is the response of your system. It is a total response. I mean, the blue one, this is a total response. So the total response will consist of the natural component, which will disappear at t equals 6, correct? So you can say that, okay, settling time equals 6. And after that, we will have only steady state, which is equal 0.6. So now we need to go to skill assessment exercise. We have this example. You have this function, t exponential minus 5t, right? So if we need to convert it into Laplace transform, so we will look into exponential minus 5t. Exponential minus 5t, it will be 1 divided by s plus 5. And because here we are multiplying by t, so we will just square it. That is it. So this is the first skill assessment exercise. The second one, find the inverse Laplace transform of that part. That part we need to use, I mean, if we need to solve this one, we need to use partial fraction expansion. So it will be, we can say that f of s equal k1 divided by s plus k2 divided by s plus 2 plus k3 divided by s plus 3 square, right? Plus k4 divided by s plus 3. K1, K2, K3, it's easy to find. And to find the K4, you need to differentiate the equation which you used to get K3. So if we need to get K1, what will be the value of K1? Multiply both sides by S and set HS equal to 0. So it will be 10 divided by 2 multiplied by 3 square. 3 square, it's 9. 2 times 9, it's 18. So it will be 10 divided by 18. So K1 will be 10 divided by 1/8, which is 5 divided by 9, right? This one. K2, if you want to get K2, so in this case, you need to multiply both sides by S plus 2, substitute S equal minus 2. So it will be 10 divided by minus 2, multiplied by minus 2 plus 1, it will be 1 squared. So it will be 10 divided by minus 2, it will be minus 5. So it will be minus 5. So K2 will be minus 5. So if you want to get inverse Laplace transform of that part, it will be 5 divided by 9 minus 5 exponential minus 2. If you want to get K3, it will be the same. If I want to get K3, so you need to multiply both sides by S plus 3 squared, so that part will disappear. Set HS equal to minus 3, so it will be 10 divided by minus 3 multiplied by minus 3 plus 2, which is minus 1. So it will be 10 divided by 3. It will be 10 divided by 3. So it will be plus 10 divided by 3 exponential minus 3t. But remember, this term is a square, so we need to multiply it by t. And for K4, I will ask you to find the K4. So it will be the same equation here, differentiate and find, similar to the example which we did before. So this is the solution for the first problem here. We got it, right? So you can start with f of t. Anyway, we solved it, right? We can go to the second skill assessment exercise. We use the partial fraction expansion, right? Partial fraction expansion. So as I told you, this one, it will be, it will be f of s equal k1 divided by s plus k2 divided by s plus 2 plus k3 divided by s plus 3 squared plus k4 divided by s plus 3. And try to find the k1, k2, k3, k4 and complete your solution. So section point 2, it's about transfer function. How can we get transfer function? Transfer function g of s is defined as the ratio of Laplace transform of the output divided by the input at 0 initial condition. So this is the definition, and this function provides complete characterization of your system behavior in the frequency domain, because this is the characteristic polynomial, and the roots of this characteristic polynomial, it will tell us if your system is stable or unstable. So, we can say that, okay, this is the block diagram of your system. The output is C of S, the input is R of S. Your transfer function, we call it G of S. It will be C of S divided by R of S, right? And if you need to get the output, so C of S will be just a cross multiply. So it will be R of S multiplied by G of S, and apply inverse Laplace transform to get C of t, if you want to get this one in time domain, and plot it in time domain. Okay, now we will take an example. So this example, find the transfer function represented by this function. This function, it's differential equation. So I will write it in a different form. So it will be C dash plus 2C equal R. Apply Laplace transform to this one. So it will be, it will be S C of S plus 2C of S equal R of S. Take C of S common factor, so it will be S plus 2 multiplied by C of S equal R of S. So we need to get G of S, which is a transfer function, so it will be the output divided by the input. So it will be this one divided by this one. It will be the coefficient of this one, which is 1, divided by the part. So it will be 1 divided by S. plus 2. If you want to get C of S, so we can see that, okay, now C of S will be cross multiply, so it will be R of S divided by S plus 2. If you want to get the response for step input, if R of T equal 1, in this case, R of S equal 1 divided by S. So we can see that, okay, C of S will be 1 divided by S multiplied by S plus 2. Use partial fraction expansion, so it will be K1 divided by S plus K2 divided by S plus 2. Find the K1. So multiply both sides by S, set S equal 0, so it will be 1 divided by 2. So it will be 1 divided by 2S. You need to find the K2, so also multiply both sides by S plus 2, set S equal minus 2, so it will be negative half multiplied by 1 divided by S plus 2. Apply inverse Laplace transform, so C of T will be 1 divided by 2 minus 1 divided by 2 exponential minus 2t. So now we can have our response in the time domain. As you can see here, the time domain. Time response consists of forced component, which is 1 divided by 2, minus natural component, which will decay over time. So if you want to plot the response, just put it in Python and try to plot your response. And as you can see, that the forced component is 0.5. So the forced component is 0.5. So when we reach a steady state, we need to, our response should equal to 0.5. And the exponential part here will disappear over time, right? This exponential part, it will decay. Okay, so we can go to the second example. I mean, for this specific problem, I told you that, okay, this is my open loop response. This is my system, 1 divided by S plus 2. And we try to plot the response here for R of T equal 1 for step input. R of T equal 1, which is unit step. Unit. So the response will be like this one. And as you can see, if you increase the input here, you will still also get some steady state error. If you want to overcome this steady state error, you need to use closed loop system. So we will just close the loop. As you can see here, this is my system. And I will add here a controller. And this controller will be just amplifier, power amplifier. This one is just power amplifier, which has again equal K. And I will feed back the system response to the input. R of S equal 1 of S, or you can say that R of T equal 1. This one plus, this one negative. We will calculate here the error signal. So the error signal will be R of T minus C of T. So this error will be, we call it E of S, which is R of S minus C of S, correct? Multiply this error with the gain, and the gain will apply control signal to your system. So in this case, we can just try to adjust steady state error. So when we did that, in fact, using a K equal maybe 10, we can reduce, in fact, steady state error from 0.5 maybe to maybe 0.15, for example, or 0.1. So you can find the overall closed loop system for this system. This overall closed loop system, it will be G of S divided, it's the forward bias divided by 1 plus 1 minus G H of S. So I can draw it like this one. So if you have this one open loop, G of S, this one is C of S. We have here a summing point, R of S. The input here, it's E of S. In the feedback, we have a transducer which has a transfer function H of S. You can say that, okay, the overall transfer function will be the forward divided 1 minus forward multiplied by feedback. It will be GH of S. So it will be like this. So you can find the overall transfer function. And after finding it, this overall transfer function, in fact, we can plot it like this one. It will be like this one. T of S, the output also still will be C of S. The input will still, in fact, R of S. But this is closed loop transfer function, not open loop transfer function. So when you look into it, you will see that we have a feedback loop. We call this one feedback loop. This feedback loop, in fact, it's very important because it helps us to calculate the error. And if you can calculate the error, we can use a controller to minimize this error. So we use this feedback closed loop system. So I try to plot the response for you for K equal 100, for example. And as you can see here, when you increase K, you will reduce steady state error. Steady state error will be very, very small now. It's around less than 0.05, something, less than 5%, maybe. Correct? Because this one it's 0.9, maybe it's very, very small, in fact, right? Maybe it's 0.001 something. So when you increase K, you will be able to minimize this error, but this error will not be possible to be zero. It cannot be zero because of my controller, because here I'm using a power amplifier, and this power amplifier, it will not amplify zero input. You need to still have some input in order to amplify this small input and generate a control signal to drive your system or to power your system. So using only this kind of controller, you cannot achieve a steady state error equals zero, because if you will have here steady state error equals zero, U of S will be zero, because U of S, it's K multiplied by error. And if U of S equals zero, your system will collapse and it will go back to zero quickly, right? So it's not possible using this type of controllers. So here we have also some skilled assessment exercise. We have here a differential equation, and we are asked to find the transfer function. So we will do it quickly. So in the first problem, it's a C double dash. I will write it in different ways. C triple dash plus 3 C double dash plus 7 C dash plus 5S equal R double dash plus 4 R dash plus 3 R. So just apply Laplace transform. So it will be S cubed plus 3S squared plus 7S plus 5 all multiplied by C of S equal, the other side it will be S squared plus 4S plus 3 multiplied by R of S. We need to get transfer functions, so G of S will be the output, which is C of S divided by R of S. So C of S divided by R of S, it will be that part, which is S squared plus 4S plus 3 divided by S cubed plus 3S squared plus 7S plus 5. So it will be like this one. So we can see the solution here in the next page. So we have this transfer function. We will go to the second skill assessment exercise. Let's find the differential equation. Now we need to go into the opposite direction, right? So we need to find the differential equation. You have this transfer function. We know that this transfer function equal the output divided by the input. So it will be C of S divided by R of S. Use cross multiplication. Cross multiplication, it will be like this one. So it will be 2S plus 1 multiplied by R of S equal S squared plus 6S plus 2 multiplied by C of S. 2S multiplied by R of S, it will be R double dash plus R equal C double dash plus 6C dash plus 2C. So this is my differential equation. So now we are done, correct? So this is my, just order it, I mean, starting by C double dash in the left side, and the input will be in the right side. Anyway, now we are done with this example. So we will go to the, maybe this is the last example. So find the ramp response for the system. You have G of S transfer function, which is, again, C of S divided by R of S. And we need to find the response for a ramp input. So in this case, R of T will be equal T. In this case, R of S will be 1 divided by S squared. So that is it. So just to cross multiply in this way, or we need to just find the C of S, in fact. So from this equation, we need to get C of S. So it will be S divided by S plus 4 multiplied by S plus 8 multiplied by R of S. R of S equal 1 divided by S squared. So it will be S divided by S plus 4 multiplied by S plus 8 multiplied by 1 divided by S squared. S will cancel S. So it will be 1 divided by S multiplied by S plus 4 multiplied by S plus 8. Use partial fraction expansion. So it will be K1 divided by S plus K2 divided by S plus 4 plus K3 divided by S plus 8. Find the values of K. to find the value of K1. Cross, just take limit as S goes to 0, so it will be 1 divided by 4 times 8. 4 times 8 is 1 divided by 32S. S plus 4, so we will take the limit as S goes to minus 4, so it will be 1 divided by minus 4 multiplied by 4. 4 times 4 minus 1 divided by 16. 1 divided by 16, so it will be like this one. So the other part, it is S plus 8. So take the limit as S go to minus 8. So minus 8 multiplied by minus 4. So it will be plus 1 divided by 32, like this one. Take inverse Laplace transform. So it will be 1 divided by 32 minus 1 divided by 16 exponential minus 4t plus 1 divided by 32 exponential minus 8t. So now we are done with it. And finally, you can just simulate it as we did before, plot the response in MATLAB, and we can see the response that, okay, we have this response, which consists of forced component again, and this one will be the forced component and natural component. This forced component, it's due to the input. The input here, it's ramp. So due to the ramp, we got this response, we got this kind of response. So now we are finishing part 2 from chapter 2. So thank you very much, and see you soon in part 3 of chapter 2. Thank you very much.